Okay, your lesson for today is over the fundamental theorem of calculus. And what this is going to allow us to do is it's going to allow us to connect the two major ideas in calculus, which is the derivative and the antiderivative. So the other day we used geometry to evaluate definite integrals such as the one listed. And the way that we would do that is by graphing the function x plus 1 on the interval from 2 to 4. So I'm going to use my pencil here to sort of graph this function. So from 2 to 4, the easiest way to graph this would be to evaluate the function at 2 and 4. So if I plug 2 in for x into my function here, then that's going to give me 2 plus 1, which is 3. So I know that at 2, I'm going to have a y value of 3. And then at x equals 4, if I plug x equals 4 into this function, then 4 plus 1 is going to be 5. And so at 4, I'm going to have a y value at about 5. Okay, and so in between, I know that this is going to be a linear function. And so what I'm finding is the area of this trapezoid. And I know that the area of a trapezoid is 1/2 the y1 plus the y2, so that would be my 3 plus my 5, multiplied by delta x, which is going to be 2, and this gives me a total of 8. So geometry will allow me to find the value of this definite integral. The next day we learned how to find antiderivative. So this is the indefinite integral of x plus 1 dx, and I know from my power rule that this would be 1/2 x squared plus x plus c. So the big question for us is, how are these things related? And we're going to answer that in the next slide here. Let's see if we can figure this out. Substitute the lower limit of integration, x equals 2, and the upper limit of integration into our antiderivative. So if we go ahead and do that for x equals 2, that would be 1/2 of 2 squared plus 2 plus c. And if I evaluate that, that's going to give me 4 plus c. If I substitute in x equals to 4, that would be 1/2 of 4 squared. So I'm plugging this into my antiderivative that we got on the previous page. This is going to equal to 12 plus c. Now, what could we do with these results to get the area that we found above by using geometry? So remember, we found that the integral from 2 to 4 of x plus 1 dx was equal to 8. So the question is what could we do with these two results, my 12 plus c and my 4 plus c, in order to get 8? And hopefully you're recognizing that what could be done is we could subtract them. So I could subtract my 12 plus c, that was where I plugged in my upper bound, and I could do minus 8 plus c, 4 plus c. Let me erase the 8 and do a 4. So 12 plus c minus 4 plus c, and that would give me 8. Of course, the c's would cancel out. And so what you might notice there is that when we do a definite integral, we don't need plus c because it ends up canceling out anyway. So what could we do with the results? We could write it in a more descriptive way here. We could say we subtract from the upper limit, when we plug in the upper limit, minus the lower limit. And that would give us the same value that we got using geometry. The amazing thing is that it turns out this always works. And the steps for doing this are to, first of all, find the antiderivative, just like we did in our above example, and then substitute the upper limit or the upper bound into the antiderivative, subtract, and then plug in the lower limit into the antiderivative. And the nice thing about this is that now we can find the area bounded by a graph in the x-axis for graphs in which we cannot use geometry. And so if we look at this next problem, the integral from 1 to 2 of 3x squared dx, then what I notice is that if I were to graph this, okay, 3x squared is going to look like a parabola, and then graphing from 1 to 2 is going to be this area right here. This could not be found using geometry. I would have to use some other method, And that other method is now the fundamental theorem of calculus. So this integral from 1 to 2 of 3x squared dx is going to equal to, I'm going to start with the antiderivative of 3x squared, which would be x cubed. I'm going to evaluate that from 1 to 2. So when I draw this vertical bar, I'm saying I'm going to evaluate this from 1 to 2, which means I'm going to plug in my upper limit first. So that will be 2 cubed. Subtract and plug in my lower bound, which would be 1 cubed. And this is going to equal to 7. So pretty cool. This fundamental theorem of calculus is now going to help me find the area under a curve in which I would not be able to find the area using geometry. So another way to say that is now I can evaluate definite integrals for which geometry will not be able to help me. And the cool thing about this is that 7 is the exact area under the curve of 3x squared between x equals 1 and x equals 2. Now, symbolically, the fundamental theorem will look like this. The integral from a to b of f prime of x dx is going to equal to the antiderivative of f prime, so that would just be regular f, evaluated at b, minus antiderivative of f prime, which is f, evaluated at the lower bound a. So this is definitely a formula that you need to memorize. It is one of the most important formulas in all of calculus. Okay, we're going to spend the next couple of examples practicing using this new fundamental theorem that we've just talked about. So, integral from 1 to 2 of x squared plus 3 dx. In order to evaluate this, the first thing I need is an antiderivative. So that would be 1/3 x cubed plus 3x. And I'm going to evaluate this from 1 to 2. So, first thing that needs to happen is I need to plug in my upper bound. I usually open a bracket here and then plug in my upper bound, so 1/3 of 2 cubed plus 3 times 2, and then close my bracket, subtract, and then open a new bracket to indicate this is where I'm going to plug in my lower bound. So that would be 1/3 of 1 cubed plus 3 times 1. Okay, so continuing to evaluate this, this would be 1/3 times 8 plus 6 minus 1/3, and then minus, so what I'm seeing here is that this is minus a negative, minus a 3 times 1, so this should be a negative 3 here at the end. Okay, so that's why it's important to have the brackets, is so that you know to distribute the negative to everything. Okay, so now I'm going to combine these numbers. 8/3 minus 1/3 is going to be 7/3, and then 6 and negative 3 will give me plus 3. In order to add these numbers, they need to both have a denominator of 3, so I know that 3 is just 9/3, and 7/3 and 9/3 will give me 16/3. Okay, for the next problem, before I can find the antiderivative, I'm going to have to split this through the numerator. So doing a little bit of algebra here first, this is going to be the integral from 1 to 9 of x divided by x to the 1/2 minus 4 over x to the 1/2. Okay, remember there is no quotient rule for antiderivatives, so I've got to do this algebra first. Okay, so this will become the integral from 1 to 9. If I divide x over x to the 1/2, remember that I subtract exponents, so that will be x to the 1/2 minus, for this term, I need to move the x to the 1/2 to the numerator, which means I change the exponent to a negative, so I have 4x to the negative half. So now that I've done this algebra, I can safely take the antiderivative. So the antiderivative of x to the 1/2 will be x to the 3/2 divided by 3/2, which is the same thing as 2/3, minus 4 multiplied by the antiderivative of x to the negative half, which will be x to the positive 1/2 divided by a half, which is the same thing as times 2. And I'm going to evaluate this from 1 to 9. So this will end up being 2/3, and I'm going to put this in a bracket of 9 to the 3/2, minus, I'm going to go ahead and multiply the 4 and the 2, so that's going to give me 8 times 9 to the 1/2, close my bracket, minus, and now I'm going to plug in my lower bound, so that's going to be 2/3 times 1 to the 3/2, minus 8 times 1 to the 1/2. Okay, continuing to evaluate here. 2/3 times 9 to the 3 halves. Remember that 9 to the 3 halves is easier if you square root 9 and then cube it. So square root of 9 is 3. Cubed is 27. So this number right here will be a 27. Multiplied by 2/3 will give me 18. Minus 8 times 9 to the 1/2. So remember 9 to the 1/2 is 3. So 8 times 3 will give me 24. Minus 2/3 times 1 to the 3 halves would be just 2/3. And then minus a negative 8. So this will become a positive 8. And then just combining these numbers together, 18 minus 24 would be negative 6. Plus 8 would be 2 minus 2/3. And in order to add those, they both have to have a denominator of 3. So that would be 6/3 minus 2/3, which will equal to my final answer of 4/3. Okay, this next example, we need the antiderivative of secant squared x, and that is something that's on my table of integrals, so I just have to kind of know that one from memory. And the antiderivative of secant squared x would be tangent x, evaluated from 0 to pi over 4. So this will equal to tangent of pi over 4, plugging in the upper bound first, subtract, and then plug in the lower bound, which would be 0. And now I have to know a little bit of trig. So remember that tangent of pi over 4 is 1, minus the tangent of 0 is 0, and so the final answer here would just be equal to 1. Okay, this next example cannot be done by familiar methods. So there is no antiderivative of absolute value of 2x minus 1. If you were going to find the antiderivative of it, then you would have to split it into two different functions, because absolute value is made up of two linear functions that kind of join together at a sharp turn. And so the easier way to do a problem like this is to graph it. And so what I'm going to do is I'm going to first of all find the vertex. And the way that I find the vertex is by setting the inside of the absolute value bars equal to 0. And that's going to give me x is equal to 1/2. So at 1/2, I'm going to have my vertex. Now, this is going to make two triangles. The first triangle, to find out where the height is, I'm going to plug 0 into my x value, and that's going to tell me the y value at 0. So 2 times 0 is 0, minus 1 is negative 1, and then the absolute value of negative 1 would give me positive 1. So my first triangle is going to look like this. And then for my next triangle, that's going to happen at x equals to 3. And so if I plug in 3 to this x, 2 times 3 is 6, minus 1 is 5. And so my y value at 3 is going to be up at 5. So this is going to be the 0.35. And my absolute value is going to end up looking like this. So the area that we're looking for here is the area under this red line. So that would be here, and it would be here as well. So I notice that that is two triangles. The first triangle has a base of 1/2, so this base here would be 1/2, and the height would be 1. So that area is going to be 1/2 multiplied by the base, which is 1/2, multiplied by the height, which is 1. Plus, this second triangle has a base of 2.5, or 5/2, and a height of 5. Okay, so this height right here would be 5. And so the area of that is going to be 1/2 times the base times the height. Okay, so continuing to go here, I'm going to erase this right here so that I can have a little bit of room, or at least I'm going to try to erase it. Apparently that doesn't want to erase. No problem, I'll just go to the side here. This is going to be 1/4 plus 25/4, which will give me 26 over 4, and that will reduce to the final answer of 13 divided by 2. Okay, for the last example on this section, we're going to find the area of the region bounded by the graph of y equals 1 over x, the x-axis, and the vertical lines x equals 1 and x equals e. So if you remember what the graph of 1 over x looks like, that would be your reciprocal function. Okay, it's going to look something like this. And then the vertical lines x equals 1 would be like right here. So we'll call this x equals 1. And then x equals e would be a little further along. And so the area that we're trying to find is this area right here. And notice that this could not be done using geometry. This is not a known geometric shape. And so this has to be done using a definite integral. A definite integral is what is going to give us the area under the curve of 1 over x between that curve and the x-axis between 1 and e. So this will be the integral of the function 1 over x dx evaluated from 1 to e. Okay, so the first thing that I need is an antiderivative. I remember that this is the same thing as x to the negative 1 dx. And remember, that cannot be bumped up and divided because you would end up dividing by 0, and that's not a good thing, obviously. So this is going to fit the other rule, or a different rule, natural log of x, absolute value of x, evaluated from 1 to e. So this will equal the natural log of the upper bound, which is e, minus the natural log of the lower bound, which is 1. And knowing some things about logarithms, I know that natural log of e is 1, minus the natural log of 1, which is 0. And the final answer to this question would be 1. Okay, I want to spend the next part of the notes focusing on u substitution with definite integrals. So we have the integral from 1 to 2 of x times x squared plus 1 cubed. And so I notice that this is a u substitution problem because I have a function inside of a function. So I'm going to let u equal to that inside part, x squared plus 1. And that means that du is going to equal to 2x dx. Okay, notice that I have the variable part of that in the problem. So x dx is going to get replaced with a 1/2 du. So if I just come down here and solve for x dx, then that's going to get replaced with a 1/2 integral of du. Now, the part that I did not circle or highlight is the x squared plus 1 cubed. So this part right here is my u, and so that part is going to get replaced by u cubed. And then the last thing I want to do is change the bounds. Right now, these bounds, 1 and 2, are in terms of the variable x. I want bounds that are in terms of the variable u. And so what I'm going to do is I'm going to take this equation, my u equals x squared plus 1, and I'm going to plug in my original lower bound, which is 1. So that's going to give me 1 squared plus 1, which is equal to 2. And now that 2 is going to go up here as the new lower bound. I'm going to do the same thing with the original upper bound, which was 2. I'm going to plug that in for my x, and 2 squared plus 1 is going to give me 5. That is going to be the new upper bound of this problem, which is 5. Okay, now that I have switched these bounds to be in terms of u, I am completely done with x. I do not want to do anything more with the variable x. So all of this stuff right here is pretty much irrelevant now. I'm going to kind of just draw these dashed lines through them to indicate I don't want to do anything else with x. I do not want to go back to x. I want to basically act like this new problem over here in terms of u is like the original question. So this integral right here, I just want to act like that was the original problem from the very beginning. So I'm going to act like that's the original problem. So the 1/2 is going to stay in the front. Let me do this with a pen. That's going to go a lot better if I use pen. So this is going to equal to 1/2. The integral from, well, let me go ahead and just find the antiderivative. So let me scratch that out. 1/2. The antiderivative of u cubed is going to be 1/4, u to the 4th, and then I'm going to evaluate that from 2 to 5. So notice I'm not going back to x. I'm not using the bounds 1 and 2. This is all in terms of u. So this will be 1/8 of 5 to the 4th, plugging in the upper bound, minus 1/8 and plug in the lower bound. And so this ends up being 625 over 8 minus 16 over 8, which will be 609 divided by 8. Okay, so the key thing in these problems is that once we get it in terms of u, including our bounds, we're never going to go back to the variable x. Okay, I notice that on this example it is also a u substitution, so I'm going to let u be the part that is inside of that square root, 1 plus 2x squared. That means that my du is equal to 4x dx, and I notice that I have in the problem the variable part of that, x dx. The only thing I don't have is the 4, so I'm going to divide both sides by 4, and that's going to give me 1/4 of du is equal to x dx. So this is going to become integral, a 1/4 in the front, a du at the back, and the part that I did not highlight is my u. It is being raised to the 1/2 power, but because it's in the denominator, I need to move it to the numerator, and so the power needs to become -1/2. Okay, the last thing I want to do, because this is a definite integral, I want to change my bounds. Right now, my bounds of 0 and 2 are in terms of the variable x. I want new bounds that are in terms of the variable u. So right here, I'm going to let u of 0 be equal to 1 plus 2 times 0 squared. So 1, that's going to be my new lower bound. And then u of 2 will be my new upper bound. And plugging 2 into this equation right here is going to give me 9. That's going to be my new upper bound. Now, once I get everything in terms of u, I do not want to go back to x. So I'm basically acting like this right here is the original question. I am done with this right here. So starting from 1/4 integral from 1 to 9 of u to the -1/2 du, I'm going to put the the 1/4 in the front, since it's just a constant, and then multiply by the antiderivative of u to the -1/2, which will be u to the +1/2 multiplied by 2, evaluated from 1 to 9. I'm going to go ahead and multiply my 1/4 and my 2, so that's going to give me 1/2. Plug in my upper bound, which is 9 to the 1/2, minus 1/2 of 1 to the 1/2, and so this is going to end up being 3 divided by 2, since the square root of 9 is 3, minus 1 divided by 2, which is equal to 1. Okay, for this example, I noticed that a 3x is inside of a sine function, so I'm going to allow u to equal to 3x. That means that du is going to equal to 3 dx, and I have dx in the problem. It's right here. The only thing I do not have is the 3, so I'm going to divide both sides by 3 so that 1/3 du is equal to dx. So that highlighted dx right there will get replaced with a 1/3. Integral sign will stay an integral sign, and then du will go at the back. Now, the part that I did not highlight, the sine of 3x, is going to become the sine of u. And the last thing I want to do is change my bounds, because right now these bounds, pi over 12 and pi over 9, are in terms of the variable x. And I want new bounds in terms of the variable u. So u of pi over 12 is going to equal to 3 times pi over 12, which is going to be pi over 4. And that's going to be my new lower bound. And then my new upper bound, I'm going to take the original upper bound, pi over 9, and substitute that into my formula for u. And 3 times pi over 9 is going to be pi over 3. So that will be my new upper bound. Okay, so once again, I'm saying it on every problem. Now that I'm in terms of u, I want to act like this is the original problem. And I'm completely done with everything right here. I'm not going to go back to x. I'm going to solve that highlighted integral now that's in terms of u. So the first thing that's going to happen is I'm going to have the 1/3 in the front. The antiderivative of sine u is negative cosine, so I'm going to put my negative in front of the 1/3 and then put cosine of u evaluated from pi over 4 to pi over 3. So this will equal to negative 1/3 cosine of, I'm going to go ahead and plug in my upper bound, pi over 3, minus negative 1/3. So that's why it became a positive, because I did minus a negative. 1/3 cosine of pi over 4. Now, on a free response question, that would be perfectly fine to leave as the final answer. On a multiple choice question, we're going to need to know a little bit of trig. So I know that cosine of pi over 3 is 1/2. And the cosine of pi over 4 is the square root of 2 over 2. And if I just multiply those fractions together, I'm going to get negative 1 over 6 plus square root of 2 over 6. Okay, for my last example on u substitution, I notice right here that I have a sine of x inside of a cube. And so I'm going to allow my u to be sine of x. That means that my du is going to be cosine x dx. And notice that I have that exact thing right here in the problem. So that underlined portion in red is just going to become du. So this is one of the few problems where I don't have to rearrange because of a constant. I had all of du in the problem, so I didn't have to do that. This not underlined part is going to become u to the third power. So this sine of x cubed, that becomes u cubed right here. And then I'm going to change my bounds to be in terms of the variable u. So I have u of 0, my original lower bound, is going to be sine of 0, which is 0, and that will go as my new lower bound. And then u of pi over 6 is going to be sine of pi over 6, which is 1/2, and that will go as my new upper bound. Now, this new integral that I have right here is completely in terms of u. The bounds are in terms of u, and the integrand is in terms of u, and I do not want to go back to x. So I'm going to continue this problem like the highlighted integral was the original problem. So the antiderivative of u cubed is 1/4 u to the 4th, evaluated from 0 to 1/2. Plugging in my upper bound, that will be 1/4 of 1/2 to the 4th minus 1/4 of 0 to the 4th. And so this is going to be 1/4 multiplied by 1 over 16, which will equal to 1 over 64. Okay, on this next section of the notes, we're going to practice doing some problems using the fundamental theorem of calculus sort of in a different way. So given that the derivative of y with respect to x is 3x squared plus 4x minus 5, with the initial condition that y of 2 is equal to negative 1, we are going to find y of 3. So we don't actually have the function y, but we can still do this problem because here in method 1, what we can do is we can find y by taking the antiderivative of dy dx and then using the initial condition to find c. So namely, what that means is that I can do f of x is equal to the integral of f prime of x dx. And so that means that this will equal the integral of 3x squared plus 4x minus 5 dx. So finding the antiderivative there, that will be x cubed plus 2x squared minus 5x. And then don't forget plus c, since this is an indefinite integral. And this is my f of x. Now, to find c, I'm going to use my initial condition, which is back up here. Y of 2 is equal to negative 1. And I obviously didn't mean to scratch that out. I wanted to highlight it, so let me highlight it instead. Using my highlighter, there we go, that's a little better. And so I'm going to use that initial condition to find c. So my y value is going to be negative 1, and my x value is going to be 2, so that will be 8 plus 8 minus 10 plus c. So negative 1 is equal to 16 minus 10 is 6 plus c. So c is going to equal to negative 7. That means that my function of x, or my y equals, if you want to say it like that, is equal to x cubed plus 2x squared minus 5x minus 7. So my y of 3, like the question was asking me to find, is just going to be 3 cubed plus 2 times 3 squared minus 5 times 3 minus 7. And if you calculate that, you're going to get an answer of 23. Now we're going to work that same problem, but using another method, using the fundamental theorem of calculus. And I hope that if you look at this formula long enough, it's just a rearrangement of that fundamental theorem of calculus. Remember that fundamental theorem of calculus said the integral from a to b f prime of x dx is equal to f of b minus f of a. And so really all that happened here is that we moved the f of a to the other side of the equation so that it said what was typed there. And this is really nothing more than that new position formula that we talked about a couple of lessons ago when we did particle motion. It's just using f instead of x and v. So this is really just the new position formula. So what we kind of need to know here, and I'm going to erase this hopefully and so that I can show you something, is for this formula, we have that f of b is equal to f of a plus the integral from a to b of f prime of x dx. And when we use this formula, the a, the lower bound, is going to be the value of x that we are given. And b, the upper bound, is going to be the value of x that we are asked to find. So the order definitely matters. B, the upper bound, is going to be the one that we want. And a, the lower bound, is going to be the one that we are given. So on this problem, we were asked to find what is y of 3, so f of 3, is going to equal to, in order to use this formula, I have to be given an initial condition. So remember, we were given that f of 2 was equal to negative 1. So my given initial condition is f of 2 plus the integral of f prime of x dx. The given value of x is here. That's 2. That's going to go as the lower bound. And the desired value of x, or the x that we were asked to find, was x equals 3. And that's going to be the upper bound. Okay, so plugging in the information I know that's specific to this problem, f of 2 was negative 1, plus the integral from 2 to 3 of f prime of x dx, which was my 3x squared plus 4x minus 5. Okay, so now using the fundamental theorem of calculus to find this definite integral, I need the antiderivative, which is x cubed plus 2x squared minus 5x, and I'm going to evaluate that from 2 to 3. And this negative 1 is just floating down to the next line in each step. So negative 1 plus, now I'm going to plug in my upper bound. I'm going to do a little bit of mental math here if it's okay. So 3 cubed is going to be 27, plus 2 times 3 squared is going to be 18, minus 5 times 3 is going to be 15. Okay, so that line is just where I plugged in my upper bound of x equals 3. Now I'm going to subtract and plug in my lower bound. And again, doing a little bit of mental math, I'm going to get 8 plus 8 minus 10. And if you evaluate all of that, we end up getting the same exact answer that we did in method 1. And so method 1 and method 2 give us the same answer. We can't always use method 1, however, because we sometimes aren't able to find the antiderivative. And I'm going to explain that in this next example. Okay, so in this next example, there is no antiderivative of sine of x squared. So I can't use method 1. I have to use method 2. So if I'm looking for f of 2, I have to start from some initial condition. So the initial condition given to me in this problem is that f of 1 is equal to negative 5. So I'm going to write down f of 1 plus the integral of f prime of x dx, which is given to me in the problem. And on the lower bound, the value of x that I have is going to be the lower bound. So the value of x that I have is here. That would be x equals to 1. And the value of x that I want, which is x equals 2, is going to go as my upper bound. So this is going to equal to f of 1, which is negative 5, plus the integral from 1 to 2 of f prime of x, which is sine of x squared, dx. And I'm going to use my graphing calculator to evaluate this and get the answer. So typing this into my calculator using the Math 9 button, I get the answer of negative 4.5054. Now, what if we had been given f of 2 and we were asked to find f of 1? In that case, I would have f of 1 equals, my given is f of 2, so that's my initial condition, f of 2, plus the integral of f prime of x dx. And now this time my given value is f of 2, so that's going to go as the lower bound, and the value that I'm trying to find is f of 1, so 1 is going to go as my upper bound. So please make sure that you're careful to put the value that you're given on the bottom, okay, and the value that you want, value of x that you want, as the upper bound on the top. Okay, this next problem was a recent AP exam problem. It says let h of x be an antiderivative of x cubed plus sine x over x squared plus 2. It gives us an initial condition here that h of 5 is equal to pi, and it wants to know what is h of 2. So I'm going to start by writing down h of 2 equals, that h of 5 is my initial condition, so h of 5 plus the integral of h prime of x dx. My given value of x is 5, and my desired value of x is 2, so that will go as the upper bound. And so this is the setup to find the answer to this problem. I guess the question is, what is h prime of x? Well, if h of x is an antiderivative of this function right here, then that means the derivative of h is just the x cubed plus sine x over x squared plus 2. So this is going to become h of 5, which is pi, plus the integral from 5 to 2 of x cubed plus sine of x over x squared plus 2 dx. And this was a calculator active question, so I would use my calculator to evaluate this integral and then add pi to it. And the final answer that I would get is negative 5.8666. On this next set of examples, instead of giving me a function for f prime, they have given me a graph of f prime. So we're going to have a similar setup, but instead of using a function to find the integral, we're going to use the graph to find the definite integral by using area. So this is going to be f of 0 equals, notice that in this problem they gave me an initial condition. They gave me that f of negative 2 was equal to 5. So I'm going to start from that initial condition, f of negative 2, plus the integral of f prime of x dx. The given value of x is negative 2, so that will go as my lower bound. And the desired value of x, or the x that I'm asked to find, is f of 0, so that will go as my upper bound. So this will be equal to f of negative 2 is 5, plus, to find the integral from negative 2 to 0 of f prime, that's going to be the area from negative 2 to 0. And so that will be the left side of this triangle. That triangle has an area of 1/2 times the base, which is 2, times the height, which is 4. And so this will give me a final answer of 9. So f of 0 would equal to 9. Now, for f of 2, I can either use f of negative 2 as my initial condition, or I can use f of 0. Either one is fine. It's sort of up to you. I'm going to just go ahead and use the given value, which was f of negative 2, and then plus the integral. Given was negative 2. The one that I want this time is positive 2, so that will go as my upper bound, f prime of x dx. So this will equal to 5 plus, and now the integral from negative 2 to 2 is going to include this entire triangle, okay, from negative 2 to 2. So the area of that entire triangle will be 1/2 multiplied by the base, which is 4, multiplied by the height, which is 4. And so this will equal to a total of 13. For f of 6, I'm going to do the same thing. I'm going to start with my given initial value of f of negative 2, and then add the integral from negative 2 to 6. And again, I'm doing negative 2 on the bottom because it was given. 6 is on the top because it was the one that I want, of f prime of x dx. So this is going to equal to 5 plus the integral from -2 to 2 was my my triangle, so that's going to be my 1/2 of 4. So my 1/2 of 4 multiplied by the height, which is 4. And then if I go all the way to 6, now I'm going to be adding in that circle as well, this little half circle that is here. Now, since that's below the axis, I know that I'm going to have to subtract it because it's going to be negative, and that is half of a circle of radius 2. So that would be minus 1/2 pi times the radius squared. And so this is going to end up being 13 minus 2 pi. Okay, this next example is very similar to the last one, except instead of having to use geometry to find the areas, this problem actually already gave me the area. And so just in case it's not clear, this is the graph of f prime over here. And once again, we're given an initial condition of f. F of 3 is equal to 5. So to find f of 0, I'm going to start from that given initial condition, f of 3, and then I'm going to add the integral of f prime of x dx. Given value is going to go on the bottom, so that's 3, and the one that I'm asked to find is going to go on the top, and that is 0. So f of 3, they tell me, is 5, and then notice that integral from 3 to 0 is integrating backwards. And anytime I integrate backwards, positive areas are going to become negative, and negative areas are going to become positive. So from 1 to 3, it tells me that this area right here is 4. And typically I would think of that as being a positive area since it's above the axis. But since we are integrating backwards from 3 to 0, that's actually going to be subtracted. And so my answer here is going to be positive 1. Okay, so hopefully that makes sense. If I integrate backwards, from 3 to 0 would be considered backwards, since that lower bound is bigger than my upper bound, then I'm actually going to have to subtract that area of 4. Now, for part B, f of 7, I'm going to start with f of 3 plus the integral from 3 to 7 of f prime of x dx. And so this will equal to f of 3, which they told me was 5. And now the integral from 3 to 7 is going to be, I'm going to go ahead and erase what I did here. Actually, it doesn't look like it's going to let me erase, so just continue going here, I guess. I'll have this area from 3 to 7. Now that is integrating the correct direction, and it is below the axis. So that 9 is actually going to be a negative 9. And so this f of 7 is going to equal to negative 4. And then finally for f of 9, I'm going to again start from f of 3. I'm going to add the integral of f prime of x dx. And my 3 is going to go on the bottom since it's given. My 9 is going to go as the upper bound since it's the one I'm asked to find. And so this is going to be 5 minus the 9 from 3 to 7, and then plus the 2, which is the area from 7 to 9. And the reason that one is adding is because it's above the axis, and I'm integrating in the correct direction. And so this is going to end up being negative 2. Okay, this next problem says to help restore a beach, sand is being added to the beach at a rate, you're going to want to circle or highlight that word rate, of s of t tons per hour, where t is measured in hours since 5 a.m. That turns out to be a very important part of this problem. How many tons of sand are added to the beach over the 3-hour period from 7 a.m. to 10 a.m.? And so this question is asking me for an amount. How many tons of sand are added to the beach? It gave me a rate. And so if I'm being asked for an amount and I'm given a rate, I am going to integrate the rate, which they call s of t, on an appropriate interval. So if I want 7 to 10 a.m. and t is measured in hours since 5 a.m., then I know that 7 a.m. is represented by t equals 2, so that will be my lower bound, and 10 a.m. is represented by t equals 5, and that will be my upper bound. Now, this is a calculator active question, so I'm going to use my calculator now to evaluate this integral using the Math 9 button, and the answer I get is 255.3678. And this is the number of tons of sand that is added to the beach between 7 a.m. and 10 a.m. Okay, on this next problem, it says if f of 3 is equal to 5, so it gives me a nice little initial condition there, and it also gives me the integral from 3 to 8 of f prime of x dx is equal to 20, we want to find f of 8. So I'm going to start by writing down f of 8 on my paper, and I'm going to say that that equals to my initial condition, f of 3, plus the integral from the given value of x, which is 3, to the one that I want to know, which is 8, of f prime of x dx. And this turns out to be a really simple problem because they gave me both of these things in the question. So I notice that f of 3 is 5, and so that's just going to go here. Plus, this integral right here is given in the question. It's 20. And so that 20 is just going to go down here. And so I'm going to have here plus 20. And so my answer is just going to be 25. So the problem actually made it real easy because they gave me everything that I needed to know. Okay, this next example is going to review our properties of definite integrals and then also help our skills with the fundamental theorem of calculus. So I'm trying to find the value of this integral right here. And what I'm going to do is I'm going to use the given equation to sort of do some nice things using properties. So the first thing I notice is that there's a plus sign here. And so what that means is that I can split this into two integrals. And I'm also going to notice that this 3 is a constant. And so it can move into the front of the first integral, f of x dx, plus the integral from -1 to 4 of 2 dx, and this is apparently equal to 28. Now notice that this right here is the same integral that I'm trying to find. So that's my unknown, and I'm trying to figure out everything else so that I can solve for that. So the next thing I kind of really need to do is I need to figure out what this integral is equal to. So I'm going to do some scratch work over on the side of the paper. So integral from -1 to 4 of 2 dx. Okay, so remember, in order to do this using fundamental theorem of calculus, I need an antiderivative, which in this case would be 2x. And then I'm going to evaluate that from -1 to 4, which means I'm going to plug in my upper bound first, subtract, and plug in my lower bound. This will give me an answer of 10. Now, I could have also done this using geometry. So if I draw a nice little picture here, y equals 2 is just a horizontal line. And then from -1 to 4, I know that's not obviously drawn to scale, but from -1 to 4 gives me a nice rectangle that has a base of 5 and a height of 2. And so the area of that region would be 10. And so this means that 3 multiplied by the integral from -1 to 4 of f of x plus dx plus 10 is equal to 28. I'm now going to subtract 10 on both sides as I try to solve for that integral. So that means that 3 times the integral from -1 to 4 of f of x dx is going to equal to 28 minus 10, which is 18. And then to get the integral by itself, I can just divide both sides by 3. And so the integral from -1 to 4 of f of x dx is going to equal to 6. Okay, for our last example, I'm going to show you how to find the definite integral of a piecewise function. And so notice that this piecewise function changes at x equals 2, and this is the integral from -1 to 4. So because 2 is between -1 and 4, I'm going to have to separate this into two integrals. And so it's going to have to become the integral from -1, which is my lower bound, until 2. And from -1 to 2, I'm going to be integrating this function right here because that's the one that applies if x is less than 2. So I'm going to put that in here, 3x minus 1 dx. I'm then going to add that to the integral starting at 2 until 4, which was our original upper bound right here. And from 2 to 4, we're going to be integrating this x squared plus 1 function. And so I'm going to write that in as the integrand, x squared plus 1 dx. Okay, so now I'm going to find these integrals one at a time. So the antiderivative of 3x minus 1 is going to be 3/2 x squared minus x, and I'm going to evaluate that from -1 to 2, plus the antiderivative of x squared plus 1, which will be 1/3 x cubed plus x, evaluated from 2 to 4. Okay, continuing to go here, this would be 3/2 of 2 squared minus 2, subtract, and plug in -1, so 3/2 times -1 squared minus -1. And then plus my second integral, so that's going to be plugging in my upper bound, 1/3 of 4 cubed plus 4, minus plugging in 2, 1/3 of 2 cubed plus 2. And I'm going to go ahead and let you evaluate that on your own. If this was a free response question, this would be a great place to stop the problem. But if it was multiple choice, you would have to go through and actually do that arithmetic. Okay, hope you guys enjoyed the lesson on fundamental theorem of calculus, and I'll talk to you guys later.